Question I get asked a lot is about polytropic processes. And so I have an example problem that I wanted to work through, solving energy balances for a polytropic process. Here I have a cylinder full of gas starting at 200 kilopascals and 50 degrees Celsius, and it's expanded, so it's expanded up to 3 liters via a polytropic process. And it wants me to solve the energy balance if the polytropic process follows these different numbers. And so what we'll see when we do this is how these values of N kind of change. All of these are going from 1 liter to 3 liter, but they kind of change the process. They change how the pressure alters and how the temperature alters inside the cylinder, and also the heat transfer into and out of the cylinder. So N, what it's really doing is it's just a fitting parameter. It's an empirical value that describes the process. This expansion could happen a lot of different ways. It could happen isobarically, it could happen isothermally, it could happen adiabatically, or none of the above. It could just happen in a way. The polytropic process, the N value helps identify which way that is. And so it's kind of an empirical value. It really depends on the rate of the process being done, the rate of heat transfer, the temperature of the system, and the surroundings. All those play into what value of N might be fit to a problem. But here we're given 4 values of N, and we could remember that a polytropic process is one where PV to the N is constant. So that means that P1 V1 to the N is equal to P2 V2 to the N. We can solve for the different states. If we know pressure 1 and volume 1, we know volume 2, we can calculate an N, we can calculate the pressure. The other thing to remember is that if I solve this, we have P is equal to some constant divided by V to the N. So we can get a sense for what this might look like on a PV diagram for these different values of N. If N is 0, then the denominator here will just be 1, and pressure will be constant. So this would be N equals 0. And as N increases, we're going to have this curved line that gets steeper and steeper, right? So this would be increasing N. And we're always going from 1 liter to 3 liters, right? In the problem, we're always going to 1 liter, 3 liters. So remember that the work, the boundary work, is equal to the integral of P dV. We can see that as N increases, that the work should decrease. The area under this curve is getting less and less for that expansion process. We'll also see that the heat transfer changes for these different values. So there's going to be different amounts of heat input or output depending on what the N value is. And so we can go ahead and solve it. Now, before I jump in and solve it, what I really want to do is I start by looking at my NCES equation book and looking at some of the values for those ideal gases. So let me pull that up here. So the first thing that we should check is that we can use these ideal gas rules to solve this. So we have carbon dioxide, and we can look at the critical temperature. Our initial temperature is 50 degrees Celsius or 323 degrees Kelvin. And so we're higher than the critical temperature. And then our pressure is 200 kilopascals. It says our pressure is 200 kilopascals. And so that's 0.2 megapascals. It's much lower than the critical pressure. And so since my temperature is higher than the critical temperature and my pressure is lower than the critical pressure, the ideal gas law is applicable at high temperatures and low pressures. So I can say that this is a high temperature and low pressure for that gas. I'm probably fine to use the ideal gas law. So then I can come here and I'll pull some values from this table for carbon dioxide. So the really important ones I'm going to want to remember are the specific heat measured at constant volume. I'll use that to estimate the change in internal energy. Remember, delta U for an ideal gas is equal to mCV delta T. And it doesn't matter if this is a constant volume process or not. That will always be the formula I can use to estimate the change in internal energy. And then I'll probably want the R value, and then I should get the K value too, because one of the questions asked me to plot it when N equals K. K is just the ratio of the specific heat at constant pressure to the specific heat at constant volume. So if I divided 8.46 by 6.57, I would get 1.29. All right, so I got those values. Anytime I'm doing these calculations, I like to do them in some sort of software. We'll be learning ease in this course, which is the software that we'll use a lot to solve these thermodynamic problems, but you can use anything you want. I am going to use Excel, and the reason I like to use software is because if I make a calculation mistake, I can just fix it, and I don't have to type a bunch of stuff back in my calculator. It also holds all those sig figs in place, and so I can report my final answer to the correct number of sig figs without having rounding errors. And I'm going to have to repeat the calculations 4 times. And so this is going to just save me a lot of time if I can just copy and paste or just change a value and get the same number. So this is what my spreadsheet looks like. I went ahead and plugged in the R value and the specific heat at constant volume, and then my initial state. And I've converted a lot of these to the SI base units, except for the pressure. And because my R value is in kilojoules, I'm going to keep my pressure in kilopascals. And then the other thing I went and did is I calculated the mass. So I just used PV equals MRT, and I have pressure, volume, R, and T, so I could solve for the mass. The next thing I'll do is I can calculate the second state using that N value. So I can calculate, so we said P1 V1 to the N equals P2 V2 to the N. And so if I'm trying to solve for that second pressure, I know the second volume is going to be 0.003 meters cubed. That's given in the problem. So the pressure and calculate the pressure, and then I can calculate the temperature using the ideal gas law. Again, I know pressure, I know volume, the mass stays the same, I know R, so I can calculate the temperature at state 2. And so I can go ahead and do that for this first value of N equals 0.5. And so I have the values at all my states. Now, if I write the energy balance, it asks me to complete an energy balance for this. I know that Q in minus work out equals delta U. And so I'm going to rearrange this. I have Q in equals work out plus delta U. And I can simplify this a little bit. I know that the work out is equal to the integral of P dV. And delta U for an ideal gas is mCv delta T. So delta U should be pretty easy to calculate. For the work output, I could solve this integral, but it's going to be a little bit tricky for these different values of N. Lucky for me, these are in the NCES equation book. So I can just, I'm just going through the NCES equation book, and I can look at closed thermodynamic systems. It's right at the start of the thermodynamic section, and I'll paste in these equations here. So here it tells me the integral of P dV is the work, and it tells me what this integral looks like for both when, for most cases, except for N is equal to 1, and then if N is equal to 1, then that's a constant temperature process. We're going to have that value. And so I can put both of those equations into Excel. And if N is equal to anything but 1, I'll be using the second equation here. And if N is equal to 1, I'll use the first equation. So I can use the if function in Excel to choose based on my N value which value of work to use. The other thing I should note is these are both lowercase w. So to get them to be this workout, this capital W, I need to multiply the lowercase w times the mass. And so this is specific work, and I just need to multiply by the mass to get the total work done. So I can go ahead and type those equations into Excel, and I'll get my workout, my delta U, and then my Q in is just going to be those two values added together. So now I have the formulas that show me my workout, my delta U, and my Q in for n equals 0.5. And I can, the nice thing about having this in a spreadsheet is I can just change the n value and get the other states and the energy balances. But before I do that, I wanted to just reiterate that here we have this process for n equals 0.5. That should be my highest value of work. And I expect as I go to an isothermal process at n equals 1, and then to an adiabatic process at n equals k, and then to a another process n equals 2. As I go through these, I expect my total work, the total, I'm always going from 1 liter to 3 liters, but I expect this total area under this curve to decrease as my n increases. And I'm also expecting then to see different changes in my internal energy and different values of heat. So we'll keep an eye on that as we go through these values. So I'm going to change n to 1, and we can see that my work decreased. We also see that my delta U went to 0. That makes sense because my delta T is 0. And so my heat required also decreased. Let's go now to n equals 1.29. We'll go to n equals 1.29, which should be the adiabatic process. And we can see that, again, the work decreased. This makes sense that now the Q is 0 because it's adiabatic. And so the energy for that work had to come from somewhere. It came from the internal energy. The internal energy decreased, and my Q went to 0. This last one is going to be kind of weird because I'm going to continue down to n equals 2. So here, the work decreased again. Now that there was heat, negative heat in would be heat out. So not only did this expand, but it also cooled off in the process. And so there was a big drop in the internal energy. And so in order for this to cool off, we know from the heat transfer equations that there has to be a difference in temperature between the cylinder and the surroundings. So the cylinder is warmer than the surroundings. It's expanding and cooling off at the same time. And so that's kind of a unique process that's not isothermal or adiabatic, just like n equals 0.5 was not isothermal or adiabatic. So hopefully that helps shed some light into how these values of n, these empirical values of n, just show different types of processes that can happen to get us to the same result, to get us from 1 liter to 3 liters. And also, hopefully you saw some good problem solving strategies. I'm going to share this spreadsheet in the comments so that you can see the formulas that I used and maybe use it on your own in the future. Thanks for watching.